Hi, we're going to continue our discussion of entropy. So we're on topic 3C, absolute entropy. So it'll give us a better understanding of what entropy really is. I think it's not really right to say it's a measure of dispersal or chaos. So we'll see if we can understand it better. Okay, so topic 3C. So the key idea in this topic is that the entropy of all perfect crystalline materials is the same at T equals 0. We'll see that sometimes that's equal to 0, the entropy at T equals to 0, but not always. So that is the third law, and the third law of thermodynamics says the entropies of all perfectly crystalline substances are the same at T equals 0. And we usually assign that value to B0. So the entropy at T equals 0 for all perfectly ordered crystalline materials. And we'll see that sometimes they don't become perfectly ordered. So the third law entropy can be then measured and calculated relative to 0. So when you think about how that works, if it's 0 at T equals 0, then if we measure the heat capacity as a function of temperature, so temperature is going up as you go from the left to the right, and on this top graph, we're graphing Cp over T versus T. So we know that ds equals dq over T, and dq can usually be written as C dt, and it would be constant pressure or constant volume depending on where you're at. So if you wanted to determine what entropy is, you would make a graph, and you would graph on the x-axis T and on the y-axis CT, C over T, and the product of those two, or the area under that curve, is going to give you entropy. So the area under the curve of heat capacity over temperature graphed against temperature is going to give you the change in entropy. So if we start out and say at absolute 0 at 0, we can measure, or at low temperatures, we have to get an approximation because it's hard to measure close to absolute 0. But you can measure Cp and divide it by T, and then take that integral, and you'll get the entropy of the solid. At the phase transition, the entropy change will be the delta H of transition divided by the temperature of transition, so for fusion and for vaporization. So you can add those all together and you get what's called the third law entropy. This is showing the same thing in this graph, but it doesn't show you how the phase transitions would impact it. So I wanted to show you the other one. So at low temperatures, because we really can't measure heat capacity so well, this equation 1b tells you that to a good approximation, heat capacity can be fit as a function of T cubed, so AT cubed. So if you take that, which is the heat capacity, divide it by T, which they do right here in this justification, and then integrate over T, you end up with 1/3 times the heat capacity. So that's an approximation for those low temperatures. Down here it says it uses the Debye approximation. That's what that is, that we can't measure way down here, so we'll approximate it with something we know is a pretty good fit. So when you look in the back of your book, you're going to have absolute entropies for substances. And that'll be the entropy at the temperature of the table, and our table is 298.15 Kelvin. And it'll be at a standard pressure of 1 bar. So this is just a short table giving you the absolute entropies of some different substances, noticing that they're all positive. Everything has more entropy than at absolute zero, and gives you an idea like the size of the molecule, gives it more entropy, things like that. So you might need those numbers, but there's a bigger table in the back. So what is this entropy that can be zero at a temperature? That means that contrary to measuring a change in something, we're saying the absolute value of a thermodynamic property is zero at absolute zero. And it was Boltzmann who came up with the idea and came up with this formula that the entropy equals K, which is his constant, Boltzmann's constant, times ln of W. And W is called the weight of a configuration. It's the number of ways that molecules of the system can be arranged, yet correspond to the same total energy. So let's think about that to make sure we understand what is weight. And if you think about it in terms of pennies, it's easy to think about. So if I have 4 pennies and I throw them up in the air, how likely is it that you're going to end up with all heads or all tails? Pretty unlikely. Not because it isn't an equally probable configuration, but that it's only one configuration. So all heads is the macroscopic or macro state. It's the state that, looking from the outside, not knowing which penny is heads or tails, I would see all heads. So how many ways can you do that? Only one. Each and every penny has to be a head. So the weight equals 1 for all heads. Now let's think about another possibility. How about 3 heads, 1 tail is the microstate or macro state. So when I look from the outside, not knowing which pennies, heads or tails, I see 3 heads and 1 tail. How many ways could you do that? The tail could be the last penny, could be the second to last. Any one of these pennies could be all heads. So you would have 4 ways for that to happen. So whoops, why did I write 1? So immediately you see that rolling 3 heads and 1 tail is going to be 4 times as likely as rolling all heads. Now, if we think about the most probable state, 2 heads, 2 tails, how many ways can you roll 2 heads and 2 tails? Well, there's a formula that works for this situation, doesn't work for everything. It says that the weight will be n factorial, total number of pennies, divided by number of heads factorial, number of tails factorial. So that'll be 4 factorial over 2 factorial, 2 factorial. So 4 times 3 is 12. And then times 2 for the other part of the factorial can cancel with this. So you get 12 over 2. You can just actually do it if you want without canceling. And you get that the weight equals 6. So the most probable way for the pennies to end up is that you look from the outside and you see 2 heads and 2 tails, because those individual pennies are all different. And I think the last one is tails, heads, tails, heads. So there are 6 different ways. So it's not that it's chaotic, it's just that there are more possibilities. The weight is bigger for you to see a macro state of 2 heads, 2 tails, because those pennies have options. Up here, they didn't have options if they were going to be all heads. Total configuration number, so total configurations. So if you throw up the pennies, what are the total number of possibilities for them to end up this way, this way, this way, this way, all the ways for it to be 3 tails, 1 head, or all tails. And that ends up being that the weight of all possibilities is equal to the number of options for each penny. So it can have heads or tails, and there are 4 pennies. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Total ways the pennies can end up. And so that would mean 6 out of 16 tells you the probability that you're going to get 2 heads and 2 tails. So when you think about this idea of weights, that's really what it's referring to, is just if you're looking at a property in a molecular system like temperature, how many different ways could the molecules arrange their energy so that they'd end up with that same temperature. So how many configurations are possible for 3 molecules with a total energy 3 epsilon that could occupy equally spaced levels of energy 0 epsilon and 2 epsilon? So let's just do this one. This one right here. So when we look at it, yeah, so I wrote them all out. So 3 molecules, let's see. And I labeled them A, B, C. Yeah, so each molecule is labeled A, B, C, A, B, or C. So you have 3 epsilon total. So you could have all molecules A, B, and C, each with 1 epsilon, because that adds up to 3 epsilon. Or you could have our molecule C with 0 energy, B with 1 epsilon, and A with 2 epsilon, because 2 epsilon plus 1 adds up to 3. So I just did this by hand and figured out that there are 7 different ways that you can distribute. You have to have that same total energy, but to have different molecules have different amounts of energy. So when you think about molecules, they're like pennies. There are different ways they can contain energy. But these simple examples you can do by hand. But if you had a mole of molecules and all the energy of like room temperature, that would take forever. So Boltzmann's understanding of entropy gives you an idea of statistics, just how probable something is. And as temperature goes up, you're going to have a greater distribution of states, which we have learned just a little bit about in the Boltzmann's distribution. So if you're at absolute 0, all the molecules have 0 energy. And as you go up in energy, they can be dispersed among upper states too. So you're going to get more entropy as temperature increases. So there's a discussion right here about that fact that as temperature goes up, entropy goes up too. There's a little chemist toolkit here. You should read it. If you've forgotten your log rules, I'm sure you've used them in a few classes in chemistry. So just read that, because Boltzmann's formula says that entropy is K natural log of W. So remind yourself how you deal with logs. So when we think about the third law, it says all substances or all perfect crystals have the same entropy at absolute 0. And we assign it to be 0, but we find that sometimes that's not true. And it's because of this thing called residual entropy. So with residual entropy, you can look at something like carbon monoxide. Let's see. Doesn't say which end is carbon and which is monoxide, but if you notice this, it's not perfectly ordered, even though it's a crystalline substance. So at absolute 0, carbon monoxide would pack in as a crystal. But notice they're not all aligned correctly with their dipoles, because carbon monoxide has a little dipole. Well, what happens is as you cool it, they start to align, and you get to a point where there isn't enough energy for one to flip. So there's a kinetic barrier to flipping one of these to make sure all their dipoles are arranged so that it's plus, minus, plus, minus. And so you go to a lower temperature and it's locked into a disordered array. And so depending on what the substance is, something like carbon monoxide, there are 2 different ways that it could be oriented. So that's the number of ways is 2. So the natural log of 2 times, well, the weight would be 2 to the n. So each of the molecules can have 2 orientations, and there are n molecules, so that would be weight. But from the log rules we just saw, you can bring the n out front. So it ends up being number of molecules, Boltzmann's constant times natural log of 2 should be the residual entropy for something like carbon monoxide that has 2 orientations. And this goes through a little discussion that yes, indeed, most systems where you measure the entropy isn't 0 at absolute 0. You can look at the possibilities of orientations and come up with pretty good agreement with experiments. So go ahead and do this one. When you finish this lecture, it's very similar to the carbon monoxide one, except you have 6 orientations. So you're gonna have 6 to the n as your weight. So that is a little bit deeper understanding about entropy. And the next thing that we are going to do in the last topic of this focus, we're gonna talk about how do we, as chemists, use all of this to understand chemical reactions. So we're gonna introduce the Gibbs free energy function, which you should be aware of and have used many times.